Uh, Thanks a lot to the conference organizers for inviting me to this very nice meeting. So I'll be talking to you today about our effort on developing a detection technique uh, using what we call Raman Driven spin noise spectroscopy. So the plan is that I was also asked to say a minute about India's National Quantum Mission and particularly about Atoms and Ions platform. And then I'll talk about our facility which we are building about quantum computation with neutral rubidium atoms in optical Quasar arrays briefly. And then one of the experiments what we have set up over the past few years is a sodium and potassium cold atom mixture. And then I'll get into this particular spin noise detection technique. And if time permits, I will talk a little bit about our results on quantum sensing, that is magnetometry. So before I start the talk, I would like to thank my team members, Sagar, Anirban, Nilanjan, Sai, Augustruta. I think most of them are here. Alan, Pankaj, and Vimit have joined recently. So Mishra, Gaurav, and Shairi have completed their thesis as well. And most of the last part of the talk on spin noise I'll be talking, which was done by Maheshwar and Shairi. We have a strong collaboration with Professor Dibbendu and Professor Supurna Sinha, and Professor Sanjukta is also here. She will give a talk later in the day. So some of the recent publications related to our work is listed here. I will not be able to cover the whole of the work. So just a few words about India have announced the National Quantum Mission, and Bangalore has a strong presence with, so this has a hub and spoke model. Overall, the nominal budget is around 0.65 billion USD. And so multiple platforms are supported. Ions and atoms are actually one very strongly supported platform. So our work comes under what is known as Foundation of Quantum Computing Innovation Hub, which is also, I understand, a part sponsor of this program. And this mission initiated a few months ago. So this is the logo of the National Quantum Mission of Government of India. And this is the logo of our hub, which supports the quantum computing initiatives as well. So just another few words. So with atoms and ions, we do have a consortium. Very happy to see Professor Umakant and Professor Rejish Nath who are here. Rejish is one of the organizers of the conference. So we are building neutral atom and trap ion based systems, and eventually we also want to get into miniaturizations and various other novel direction. But right now the focus is to have usable devices for the country as well as for development. All right, so there are globally a lot of interest. In Florian Strog, there was a very nice image of the atom array, and this was I took from a recent paper from QERA collaboration with Lukin's group, MIT Harvard collaboration, where very nice single atom arrays have been demonstrated, and very nice work has been done. There is also fantastic work coming from Caltech very recently with cesium atoms with 6,000 plus highly coherent atomic qubits with high numerical aperture. As optics is becoming better and better, more scalable and high fidelity gate operations with these single atoms are being performed all over the world. And also another thing I was very interested about, and we are also trying to implement some of it, is integrating the photonic integrated circuit. In this case, here is a nanophotonic chip, which is demonstrated to clear from University of Chicago an atom array and imaging of single atoms. There are many such approaches to create scalable quantum platforms. So one connected topic of this meeting is using these atom arrays also for quantum simulation. One result which I was very, very intrigued about is the Hamiltonian engineering, where the different geometry of the atom arrays, whether it's square, triangular, hexagonal, so actually leads to various different ground state solution. This and multiple papers which followed, you can pick up, where something like a very hard problem of checkered board phase, which were very nicely demonstrated with a 16 by 16 array. And I'll not get into detail because these works are already quite celebrated and extremely promising. All right, so one of the key work which is needed for this is entanglement generation between the atoms. So this is typically done with these atoms. So typically these atoms are transported to a region where Rydberg excitations are used to create entanglement between the atoms within the blockade radius. And then there are lots of work globally. I just wanted to highlight that in RRI, as well as a collaboration with Professor Rejish Nath, there had been very nice work recently, and they're progressing with this Rydberg excitation, Rydberg blockade physics, and so on. And I assume Professor Sanjukta will give a talk on this direction towards the end of the day. And so one idea is that once this entangled pair is generated between atoms, one is identified as a control atom, another as a target atom, and then the quantum gate operations are performed for the 2-qubit using this Rydberg excited system. So the entanglement is generated via the Rydberg excitation. And again, some very nice work globally, where this entangled pair are transported physically, and then it is shown that the entanglement survives, and various future work is done. Okay, so just again, strictly for students, experts, please excuse me. So the atom traps are created using that strongly focused optical tweezers or optical dipole trap, where far off resonant light is focused onto these already cooled, laser cooled atoms, which was also shown nicely in Florian's talk. And then, for example, here, one of the very old picture from my lab, where this focused laser onto this cold atom and then transfer into that optical dipole trap. This is not that strongly focused. This is something like 100 micron, if I remember correctly. And then you can see after some time, when the cold atoms are allowed to go out of the trap, the atoms trapped in the tweezer are very nicely seen, a dipole trap, and the rest are falling out. So we make continuation of this work by having an array of such traps. This array is typically generated using two devices in our lab. One is called a digital mirror device, and another is called a special light modulator. So both have their advantage and disadvantages. And then it's an hologram which we generate, and then the light which is falling on the hologram, that is imaged onto the atom using a microscope objective, and some initial results what we had done. So this is one of our machine where the atoms are trapped in the vacuum chamber here, and then these atoms right now we are working towards transferring into this uniform special user array. The idea is also eventually to use a Rydberg excitation with 1013 and 420 nanometer, and towards the defect-free array generation and so on. This is a work in progress where the laser system and vacuum systems are installed. We are working towards a scalable architecture. So these are some preliminary results, not really single atom yet, means we're just proof of principle. So these are a few tens of atoms, and we were just trying to play around with our microscope objective to see that how this kind of system. Okay, so I'll switch over to the other work, what we do. So we have a sodium and potassium two-species machine where high flux potassium as well as sodium two-dimensional magneto-optical trap loads simultaneously a 3D mode. So we managed to capture in excess of 10 to the power 10 atoms of potassium 39. We do have provision to load potassium 40, which we have not started yet, and sodium 23. These numbers are a bit less than potassium. We are trying to now push it with a new laser to get it at the same level. And then we also have a magnetic transport stage where these atoms are transferred adiabatically from the magnetic trap in the common 3D mode to the science cell using a series of magnetic coils where the currents are transported from one coil to another, and then eventually the atoms arrive here and where we are pushing towards nice science results. So one thing right now we have been doing recently is to look at photoassociation of these potassium and sodium potassium, where we can, for example, go to one of the photoassociation potassium star or sodium potassium star kind of a molecular energy levels, and then this particular case, once the photoassociation laser is strong enough, the atoms get into a molecular state and then they boil out of the trap, or the molecule itself leaves the trap. So that's why there is a loss of signal from the trap. This is a trap loss kind of an experiment. But we do something else with this molecular interaction. So we kick these atoms from the center of the trap, and then we look at their response function, the position response function of these atoms. So initially we started at the beginning days to just look how these atoms are moving, Raman Driven motion in the trap, and then eventually recently what we have shown is that when we do this kind of light assisted tunable interaction using a photoassociation laser, how this profoundly changes the position response of this gold atom. So the general idea of the trap is that we give a kick and we look at the motion of the atoms in presence and absence of the photoassociation between the atoms. And what we see is that a very fundamentally different motional behavior of these atoms. What we understand is that once these atoms are forming kind of a temporary or very short-lived molecule pair, so that also leads to some kind of a dipolar interaction which drags along all the atoms when we kick a few of them. And that actually is the reason why there is a kind of a collective motion, even when we are not looking at a many-body physics yet, because this is far above the Bose-Einstein phase transition. So that's of our interest to look into what happens at the many-body region. So this is where we just wanted to show, just going away of the photoassociation resonance, the response function is, so this is a signature of a strongly damped response of these atoms, whereas on resonance, we do see a strong collective oscillation of these atoms. So these are some results. I thank also our theory collaborator, Professor Supurna et al. For the help with the Langevin equation based model. And so what we have also done recently, this I have not included here, is look into the same effect when we have an interspecies interaction with sodium and potassium. And then there also we do see a profound effect of the position response function changing with the interaction. So we are also interested what happens when such an interaction. In this case, we would also like to introduce the interaction via the Feshbach resonance, whether there is a fundamental change in the position response, because this is important, because this also adds to the depth of knowledge about the transport properties of the atoms, either single particle level or many. All right, so by now, I think many great talks in this meeting convinced everyone that cold atoms are great, with one serious limitation, that detection. And typically, the detection is state of the art is fluorescence or absorption. And fluorescence takes a long integration time, for good signal to noise ratio, and absorption also requires larger number of atoms, the better is the signal to noise ratio and so on. And moreover, both are destructive imaging. So one really destroys the state of the system. And one idea how to make non-demolition and fast detection with good signal to noise ratio. This is a perennial question. So I remember in MIT, phase contrast imaging was proposed a long time back. There was lots of work on Faraday rotation detection from the cold atoms, even from optical lattice and so on, and continuous efforts are going on. So I will talk about one such effort from RRI, so where we are looking at the spin measurements of atoms with megahertz refresh rate. So some ideas are also borrowed from Raman's work, so that's why we name it Raman Driven spectroscopy. The general idea is there's an atom naturally would be fluctuating between its spin states in hyperfine, in presence or absence of magnetic field. Actually, in absence of magnetic field, these states are all degenerate. So it is more natural that these atoms will be fluctuating from one state to another. There are various reasons. It can be due to thermal bath coupling, quantum fluctuations, spin exchange collisions, all will lead to spin fluctuation. Even there can be spin fluctuation between the different hyperfine states as well. All right, so how to detect that? What we do is that, first of all, just a detour. If you just want to detect the Faraday rotation, it's fairly easy from a bunch of cold atoms, and people have demonstrated even a single atom Faraday rotation is significant enough to detect. So this was some data we took for a few thousand atoms Faraday rotation as we sweep the Faraday probe light in presence of a magnetic field. So one basic idea is that when we couple a linearly polarized probe light between the different magnetic state, the right and left circular polarized components are actually with different detuning, and that leads to, as the atoms fluctuates from one state to another, it hops from -1 to 0, 0 to +1, and so on. It causes a overall Faraday rotation fluctuation of the probe light, and that can be detected. And for example, in presence of a magnetic field or not magnetic field, it's very easy for us to see this detection of the, it's a simple polarimetric detection scheme. So another small detour, you don't need to measure a quantity. What you need to measure, for example, here, if you want to measure resistance, there is no need to actually measure the current and voltage. One can also measure the variance of the voltage across the resistance and apply the Johnson-Nyquist noise criteria, and the resistance can be measured very well. So Faraday rotation is not something what we are going to measure. We're going to measure the fluctuation of the Faraday rotation. There is an advantage because that is a technique which is what I will call the common mode rejected. Because there can be polarization rotation due to various other things. So what we do is that as these atoms fluctuate from one state to another, and we send a probe light, and then usually if they're in one state, there is a Lambda precession, and if they go to another state, there is a different signal, and that actually gives rise to, for example, corresponding frequency domain signal of the magnetization fluctuation. Please see that this is not average magnetization, this is a mx of t, mx of 0 average, and then we take a Fourier transform, and that is the overall total signal of this so-called spin noise. And another way to show this is that suppose there are a bunch of atoms and we are looking at this Faraday rotation fluctuation, then it actually shows up like this. Of course, one thing I was not telling very clearly, this is a weak measurement, it's a spin projection measurement, it's not in Faraday configuration, the magnetic field is not applied co-propagating to the K vector, it's actually perpendicular to the K vector. And so this is a detail which actually helps us to make this non-invasive detection. So, okay, so one of the first thing we did from a vapor cell, and we did see a very nice and very narrow spin noise spectrum. This is in the width is typically few tens of kilohertz compared to an optical measurements where these are typically few megahertz as well, few tens of megahertz as well. So this is a very precise measurement. And we went on to measure at a very high field the spin fluctuations from different states, where even the nuclear spin contribution allows for the detection of the separation of different atomic spin state, and that allows for already implementing this as a magnetometer. We had also shown later on that how this can be used as a direction of the field measurement as well as a time varying field measurement. So this can also be a magnetometer with fast changes. I'll not tell detail about this. So what we did to enhance this signal is actually also to drive the spin states using a 2-photon Raman drive. So this is by using pi and sigma polarization component of light generated with two separate acoustic modulator, and then we made a spin oscillation between one state to another, and the spin oscillation is the same signal which shows up. I'll show a time domain signal later, but in frequency domain signal we can see a very narrow spin oscillation, and this was something just to demonstrate that we can see the envelope of the spin noise signal enhanced by the spin drive or so-called Raman drive. If we drive very strongly, then one can see that the signal increases by something like 1,000,000-fold, which allows us to detect a very low number of atoms in cold atom system. So this is the general idea. So where we have implemented both in a vapor cell and in the cold atom. So where this spin drive or the Raman drive allows us for this kind of a very clear signal to noise ratio. So one signal is that as we scan the magnetic field, we can see a spin resonance which can be seen, as well as a direct time domain signal where there is a strong spin coherent signal which we can detect using the same polarimetric method. All right, so we will in the next few minutes, I will just try to say that how do we use this for probe a small region in this cold atom system, what we have. So what we do is that we have this atom source which loads a magneto-optical trap where we do the spin drive and then send a probe light to actually measure, and we focus the probe light so strongly that we make sure that there are very few atoms, because this is done in a magneto-optical trap. So the densities are pretty low. In potassium particularly, it's in our focal spot of 30 micron, there are hardly a few atoms. So in that case, we can actually see a time domain signal, and since we also apply a bias magnetic field, or we just shift the center of the cloud away from the zero of the magnetic field. So there is always a bias magnetic field which allows us to see a spin oscillation signal. And one thing I just wanted you to notice that these spin oscillation signals are actually can be not even averaged of the order of a microsecond. So several oscillations, because it depends on the Lambda frequency. So it's actually pretty high signal to noise ratio at time scales of megahertz refresh rate. So this works well for atoms. Of course, I don't know, might also work well for ions as well. It's non-invasive because the probe light is shifted from the atomic resonance by something like 2000, something like 2000 gamma. So we are very far off resonant, and then this is also microsecond detection. We could track the Raman driven spin noise signal even at a very low atomic density, and this allows us for a high signal to noise ratio as well. So this, we had an estimate that we could see a spin driven or Raman driven spin noise signal for as low as something like 50 atoms. Of course, the dream is to shine such a probe on a single atom array and then detect directly, continuously, and some work. Of course, we were struggling a lot a few years ago to detect even a million atoms. So we made a lot of electronics and other progress. So I don't see why not we can go to a single atom detection. And that might be a real time, because we do see while making these measurements that not even a single atom is knocked out of the trap. So that means that it is really a totally non-invasive detection technique, we can claim. So, of course, it was a good question from the referees. Wanted to know that what we are seeing is really this. So we actually did a density estimate by an inverse-Abel transform from the fluorescence image, and then we have shown that our Raman-driven detection scheme actually overlaps. So that means we are really detecting the density profile of the atom. So we were just moving the atom using an external magnetic field across the probe light, same as moving the probe or scanning the probe as well. All right, so there was some, just wanted to highlight that this scheme, I am very happy that it might be a very useful scheme. Okay, so if we have some more minutes, I see, so then I can also see that it's also a magnetometer. So in that case, we know the magnetic field, so we have a detection at a particular frequency. But if we know the frequency of detection, then it can be used as a magnetometer. So what we have first shown is that the position of the peak itself is a Larmor precision, and since the peak can be determined with a very high precision because it's an extremely narrow signal, so we could first show that this is, we calibrated this as a magnetometer operation. So that is like at a low field, it performs pretty competitive with traditional Raman Driven, optically pumped magnetometers in atoms. And at high field, where I think the real advantage lies, so most of the atomic magnetometer stops working at high field because the signal saturate. In our case, since we are looking at a noise, not overall Faraday rotation, the signal almost never saturate. We can actually even see the bright Rabi splitting of these atomic transitions. So these are all like the small bright Rabi splitting, and then we can model using the bright Rabi splitting formula, and from there we get even a better resolution. So this is a simple experimental data superimposed on the bright Rabi splitting using the atoms, and using that we can also do, for example, a DC field resolution measurement. These are all initial measurements where we had a probe magnetic field which we varied, and we actually saw how the signal of the Raman driven spin noise signal changes. And from there, we had done this repeatedly and then estimate. Okay, so this is something what you have shown. So we had estimated that we have a overall resolution of around 30 picotesla. So that is a integrated resolution. And then we also did what is known as a AC magnetometry. We had a noisy magnetic field, and that noisy magnetic field was creating various Raman peaks or spin peaks in the spectrum. And from there, we can estimate what is, first of all, the resolution as well as the response of these systems. So right now, we report a modest sensitivity of the order of few tens of picotesla per square root of hertz, which is good for various application, particularly considering that this is a field deployable in case of a vapor test system, of course not a cold atom system, but it doesn't require shielding because it's kind of auto shielded itself. But we are actually a bit affected by the phase noise between the acoustic modulators. So right now we are trying to implement a phase lock loop so that these lines are getting even narrower. We have some evidence, so we can perhaps soon report 1,000 times better sensitivity with the same bandwidth. So that is one of the target with this kind of magnet. So some other things, very preliminary initially. So we do see this kind of spin noise signal, as I explained before, in presence and absence of another species. We don't fully understand these results yet, but I have a suspect that this is because the interspecies spin-spin interaction. We do have a shift of the Raman Driven spin noise signal. This is a work which we want to do, but I would really love to do this work in a BEC mixture where the signals are expected to be much stronger. And okay, so I almost come to the conclusion. So I have talked to you about the spin noise spectroscopy platform. So this is a minimally invasive probe, not really a fully quantum non-dimulation, because we still do have a little bit of a projection noise. And then Raman Drive allows us for controlled amplification of this intrinsic spin fluctuation. I did not talk to you about some of the recent results. We do also see a cascaded lambda system, not just a 2-photon, but a 4-photon or 6-photon process. So we call it higher order harmonics in coherent spin dynamics. So this is something what we are working on. So there is also real-time probe, call it density probe. I hope that one day it can be a single atom detector probe. And this is also a non-invasive diagnostic. And what I just wanted to highlight is that these atomic systems are very nice for both as a sensor as well as for the computation and other progress. So I think I almost come to the end of the talk. So if you do ask questions, I'll be happy to.
Thank you. Are there questions? Because Pankaj, maybe you can help.
Yeah.
Thank you. Very, very nice talk. For the magnetometer, when you say that might be spin exchange collisions, have you varied the density of, do you have any signature of?
Actually, for the higher order spin dynamics, we did have a study. So the work is on archive now. So we are discussing also. So there is a density dependence, and rightly so. Means why there should be a density. But we do see the density dependence is not very critical. Means because since we are collecting the signal from a very, very small region, and the collisional timescales are different than the spin oscillation timescale. So I suspect that that kind of protects the spin noise signal from having a density effect. But at some level, of course, the spin exchange will clearly have an effect on the density. So another thing with one of my collaborators, what we discussed, suppose we have two different types of magnetic interaction, and then it kind of changes the local magnetic field, the presence of another atom in a particular magnetic orientation. So that changes the local value of the Larmor frequency. So it might be an explanation for the shift in the peak, but not sure. We need to do a lot more studies on that.
Okay, great. And at some point, maybe even magnetic dipole interaction.
Yeah, absolutely. Yeah. No, I'm sure about that. Yeah.
Any further question? Hossein, there is no further question. If you have.
Okay, then with that, I guess join me in thanking Saptarishi for a nice presentation. And I guess this is India, so I would say enjoy the tea break.